This is part 2 of the video on Bohr's atomic model. It's just a continuation. So I just wanted to show you something really amazing. So back to postulate 4 from Bohr's model, which states that angular momentum, MVR, is quantized. Okay, just keeping that here for now. After Bohr's model, there was another atomic model proposed by Louis de Broglie. Louis de Broglie was a French physicist and also a French prince, and he did some groundbreaking work in his 1924 PhD thesis in physics. Let me show you what he did. So what he did was he wanted to find a way to... So Bohr's model had its limitations, in the sense that Bohr's model but still had its limitations, as I mentioned. The fact that electrons are still moving. Electrons moving, they emit energy, and they should technically spiral into the nucleus. There was still that issue, and so de Broglie wanted to rectify that somehow. So I'll show you a simple approach. So knowing that HF, knowing that the energy. Knowing that energy is quantized, electromagnetic radiation, aka light, is quantized, he equated that to, so E equals HF, that's the Planck relation. Energy is also given by E equals mc squared, Einstein's equation, where m is the mass of an object, c is the speed of light, it's a number. And using c equals f lambda, okay, so this is from another video that I made, but we're putting here c instead of v. Okay, because we're dealing with light electromagnetic radiation. Let's plug this in. So F is just C over lambda. Let's plug that in. So we get HC over lambda is mc squared. Rearranging for lambda, we get this. Okay, the C's cancel out. We get lambda is equal to H over mc. This is the breakthrough. Lambda is... So the left-hand side of the equation is a wave property. It's the wavelength of a wave, right, in meters, let's say. The right-hand side of the equation shows particle property. Okay, that's m for mass for an object. So this equation is something really profound. It shows that there's a wave-particle duality for any object, let's say an electron. So an electron is no longer thought of as just being a particle. It's also a wave, according to de Broglie. Remarkably. And this has been verified by experiments. There was an experiment conducted in the States by two physicists, Davison and Germer, in 1927, and also, ironically, by J.J. Thomson's son, George Thomson. So J.J. Thomson showed that electrons are particles, and then his son came along in the 1930s, 40s, and showed that electrons are actually waves. And it turns out they were both right. Okay, everything possesses this wave-particle duality. Okay, electron, depending on what experiment you do, an electron is either a particle or a wave. And de Broglie also won a Nobel Prize for this. Now here comes the amazing bit, something which blows me away till this day, every time I teach it. De Broglie, to explain the stability of electrons around the nucleus, de Broglie came up with this condition. Now that the electron is a wave, according to de Broglie, and having this picture in our heads that the electrons orbit the nucleus in like a circle, in order to explain stability, the wavelength of the electron must be some integer number, okay, fitting around the circumference. So 2 pi is the circumference of the circle. So this condition must be satisfied in order to describe a stable electron. Okay, some whole number of wavelengths to fit around a circumference. So let's plug in this here. Lambda is equal to H over mc. Okay, we'll use V in this case instead of C for an electron, because C only applies to light. We get this H over mv. So lambda is equal to H over mv, 2 pi r. If we rearrange this, we'll get this. if we go back here, that's literally Bohr's quantization condition. Absolutely amazing. Straightforward maths, just a bit of algebra, substitution. And de Broglie arrived at this result. So he pretty much verified Bohr's fourth postulate on the quantization of angular momentum. Okay, and that's progress right there. That's how science works, really. We build upon others' work.